welcome back to the course on econometric modeling module 14. So, till module 13 I had discussed specifically in this part, that is in part 3, the first 3 modules focused on multiple regression analysis or introduced the multiple regression analysis from different dimensions, including its measurement, properties, assumptions, and then certain other things like inferences and adjusted R square. Now, I will be talking about problems of multicollinearity. This is actually not a classical or not a part of the classical linear regression model or not a part of the assumptions under classical linear regression model, but it is a part of the Gauss Markov theorem. If you remember, Gauss Markov theorem assumes that there should not be any collinearity among the independent variables, specifically perfect collinearity among the independent variables. Now, this issue is actually addressed here in the problem of multicollinearity. So, this we again begin with our population model, which is y equals x beta plus u. Now, x is n by k matrix, the rank of x if less than k, then uniqueness of the estimated parameters breaks down. Now, we are specifically talking about the problem of perfect multicollinearity. What happens? If rank of x is less than k, then we can get x multiplied by a equals to 0, where a is any constant. So, we have found beta hat such that y minus y hat is minimized where x beta hat equals to y hat. So, this is the standard thing that we have minimized the residual sum of square in order to get a beta hat, and from there we have x beta hat equals to y hat. But since x a is equals to 0, we can also write x beta hat plus a equals to y hat, right. Therefore, to get unique results we need to have the rank of x equals to k, otherwise this problem of uniqueness will break down. So, columns of x are linearly independent if the columns of x are linearly dependent such that there exists some theta of dimension k by 1 for which x theta equals to 0, then the problem of OLS breaks down. We do not get beta hat, because if OLS gives us beta tilde, then x beta tilde equals to y hat, but x beta tilde plus theta is also equals to y hat, and that is why we do not get unique estimates, right. So, this is the problem of perfect multicollinearity. Perfect multicollinearity, most of the statistical packages actually do not even provide results if there is perfect multicollinearity. So, this is a problem which is actually taken care of by today's statistical packages which are used to estimate multiple regression models. But the problem is actually of concern when we have simple multicollinearity. So, not perfect multicollinearity, but multicollinearity of some level, which actually implies highly correlated regressors. Columns of x are linearly independent, so not a problem. Therefore, beta hat can be estimated, but the standard error of beta hat becomes large and t statistic becomes small. It becomes difficult to prove statistical significance. This is often referred to as the problem of multicollinearity. In order to prove and assess what kind of problem multicollinearity causes, it should be noted first that the R square studied so far is conventionally known as the centered R square. So, now we are going to introduce something which is called uncentered R square and explain that what kind of problem we might associate or might have or might associate with the problem of multicollinearity, right. So, we define the centered R square as this. This is centered around the mean value of the series. So, y hat minus y bar prime multiplied by y hat minus y bar, this is my explained sum of square, and what it is explaining? It is explaining the deviation of the estimated y hat from the mean of the series y, right. So, it is centered around the mean values, and that is why it is called centered R square. Similarly, in the denominator I have y minus y bar prime multiplied by y minus y bar. So, the original values are also centered around their mean values. This is our total sum of square. Now, uncentered R square is calculated as y hat prime y hat divided by y prime y. So, you can see that it is not centered around any value, and that is why it is called uncentered R square. It can be denoted by R square UC or use R UC square. Okay. Now, let us split the dependent variable or the matrix of dependent variable x into two components. One is one single variable x1 and the rest are included in x2. So, x1 is a n by 1 vector. There is only one variable, of course corresponding to that variable I have n observations, and x2 contains n by k minus 1 variables, provided that I have total k variables including the constant term. So, x2 is of dimension n by k minus 1. We need to show that if x1 is highly correlated with x2, that is x1 almost lies in the column space of x2, then standard error of beta 1 hat will be very large. If x1, that is this variable, is highly correlated with all the other variables or some of the other variables, then the standard error of beta 1 hat will be very large. And what will be the problem? If you remember, while discussing T inferences in the context of simple regression analysis or even in the context of multiple regression analysis, what do we have? In the numerator, we have beta hat minus the null hypothesis value of the population parameter beta divided by the standard error of beta hat. So, if standard error of beta hat becomes large, it goes up, then if standard error of beta hat becomes very large, then the entire things becomes very small, and then it is actually difficult to reject the null hypothesis, because it will fall in one of the or most often the left side rejection region. Now, to show that how these things happen, that why presence of high correlation between x1 and the other variables contained in x2 causes a problem or causes the problem of multicollinearity, we will first consider or reconsider the projection matrices that I had discussed in the previous module, right. So, I defined one orthogonal projection matrix M, which was I minus x into x bar x inverse x prime. Similarly, I have the orthogonal projection matrix M2 here defined in terms of x2. So, I minus x2 into x2 prime x2 inverse x2 prime. Following the Frischwall-Lovell theorem, we run a regression of x1 on x2 and collect the residuals M2 x1. Okay. So, we are trying to find out how much of x1 is explained by x2, that is all the other independent variables. In order to do that, first running a regression of x1 on x2 and collecting the residuals. Then we run a regression of y on x2 and collect the residuals m2y. Now, if we regress m2y on m2 x1, then we will be obtaining the estimated value of beta 1 hat. Okay. Now, why we are taking this indirect route following Frischwall-Lovell theorem? Because we have a purpose to prove that this correlation between x1 and x2 can be troublesome for for testing the significance or while testing the significance of beta 1 hat, right. So, we write beta 1 hat as, see, you remember beta hat is x prime x inverse x prime y, where x is the independent variable, y is the dependent variable. So, here in this context, my independent variable is m2 x1 and my dependent variable is m2 y. So, in a similar fashion, when I estimate beta 1 hat, x prime x inverse will be replaced with x1 m2 x1 prime, which is x1 prime m2 x1. So, again m2 x1 whole inverse multiplied by x1 prime m2 y. So, this actually is x1 prime m2 prime m2 x1 inverse x1 prime m2 prime M2 y, right. If you remember, M2 is a symmetric matrix. So, M2 prime M2 is actually M2 M2 and they are also idempotent matrix. So, M2 M2 is actually equal to M2 and that is why we have this expression and this expression, right. Now, if I consider variance of beta 1 hat, then again by drawing analogy, if you remember, the variance of beta hat is sigma square x prime x inverse, right. So, similarly it will be here, this is my independent variable. So, it would be M2 x1 prime M2 x1 whole inverse and M2 x1 prime M2 x1 whole inverse is this expression which is equivalent to this expression. So, that is how we have sigma square u x1 prime M2 x1 inverse. Now, sigma square u, and after that I replace the value of M2. I just for your convenience write the expression of M2 here. M2 is I minus x2 prime x2 inverse x2 prime, right. So, when I replace the value of M2 here, I have x1 prime multiplied by I multiplied by x1. So, x1 prime x1 and then this expression is coming in between x1 prime and x1 whole inverse. Taking out x1 prime x1 common out, I have 1 minus the whole expression here divided by x1 prime x1. Okay. Now, the uncentered R square from a regression of x1 on x2 will be x1 hat prime x1 hat divided by x1 prime x1. This is simply because the uncentered R square from a regression of y on x, where the population model is y equals x beta, we had written that the uncentered R square is y hat prime y hat divided by y prime y. So, in a similar fashion, when we are regressing x1 on x2, then our estimated x1 will be denoted by x1 hat. So, we have x1 hat prime x1 hat divided by x1 prime x1. So, similar to y hat equals to x beta hat equals to p x y, where p x is this, where we can have another projection matrix and that is p2. So, p2 m2 is actually I minus p2, the way m used to be equals to I minus p. So, this is how we define p2, another projection matrix, and if you remember that p x y equals to x beta hat, right, equals to y hat, p x y equals to y hat. So, now this is something which we are going to utilize next. So, x1 hat prime x1 hat will be basically p2 x1 prime p2 x1. Okay. Since y hat equals to p x y, x1 hat will be equals to p x2 or rather p2 x1. So, p2 x1 prime multiplied by p2 x1, right. Now, expanding, I have x1 prime p2 x1, which is x1 prime p2 x1, and now we replace the value of p2. So, this is the value of p2 or expression for p2. So, x1 prime x2 prime x2 inverse x2 prime x1, right. This is what I have got for x1 hat prime x1 hat, right. Now, this was my variance expression in the previous slide. I have just rewritten it here, and then you can see that this expression is exactly the expression here, which is x1 hat prime x1 hat. So, I can always write it here. This is in the bracket, I will be having 1 minus x1 hat prime x1 hat divided by x1 prime x1. Now, remember, this was actually the uncentered R square when we are regressing x1 on x2. So, this expression is replaced with uncentered R square u c, and the rest of the things remain the same. We call it equation 1. So, the above expression shows that the variance of beta 1 hat depends on 3 factors. First of all, the error variance, then the second thing is x1 prime x1, which is the total sum of square when we are regressing x1 on the rest of the independent variables, and the uncentered R square, So, these are the three things on which the variance of beta 1 hat depends. Note that R square U c can also be denoted by R j square, where it refers to the R square obtained by regressing any independent variable j on the rest of the regressor. We can also call it auxiliary regression of x 1 on the rest of the independent variables. So, in equation a larger sigma u square means larger variances for the OLS estimators. I show you the expression once again. Now, this has a inverse, right, which means this actually can be written as sigma square u divided by x 1 prime x 1 into 1 minus r u c square, right. So, sigma square u is in the numerator, x 1 prime x 1 multiplied by 1 minus r u c square is actually in the denominator. So, larger sigma square u means larger variances for the OLS estimators, because more noise in the equation makes it more difficult to estimate the partial effect of any of the independent variables on y. This is reflected in higher variances for the OLS slope estimators, right. Second, the larger the total variation in x 1 is, the smaller is variance of beta 1 hat. So, if you remember, x 1 prime x 1 measuring the total variation in x 1 is in the denominator. So, larger the value of the total variation in x 1, smaller will be the variance of beta 1. Thus, everything else being equal, for estimating beta 1, we prefer to have as much sample variation in x 1 as possible. Now, remember that y prime y was termed as total sum of square. Drawing analogy, x 1 prime x 1 can be called total sum of square 1, that is total sum of square when we are regressing the first variable or variable x 1 on the rest of the independent variables, and generalizing it to the jth independent variable, we may call it TSS j. Although it is rarely possible for us to choose the sample values of the independent variables, there is a way to increase the sample variation in each of the independent variables, increase the sample size. So, in fact, when sampling randomly from a population, TSS j increases without bound as the sample size gets larger and larger. This is the component of the variance that systematically depends on the sample size, and that is why this problem can always be handled or managed by increasing the sample size. So, this is a systematic component which can be actually handled by increasing the sample size, because R square measures goodness of fit. A value of R j square close to 1 indicates that most variations in x j is explained by the rest of the independent variables, say x 2. This means that x j and the rest of the variables or some of them are highly correlated. So, higher the value of R j square, it is close to 1, which implies that x 1 is actually explained by the rest of the independent variables, right, which implies that these independent variables are highly correlated. If R j square increases to 1, then x j would mostly lie in this column, in the column space of x 2, and variance of beta j hat will be very large. Thus, a high degree of linear relationship between x j and x 2 can lead to large variances for the OLS slope estimators. Alternatively, for a given sigma u square and TSS j, the smallest variance of beta j hat is obtained when R j square equals to 0. See, a small variance of beta j hat is a desirable property, even though multicollinearity actually does not violate the assumption of efficiency, but because of multicollinearity, variance of beta j tends to increase. So, this is not a desirable property. Alternatively, when R j square is actually close to 0, then this implies that very little of x 1 is explained by the other independent variables, right. X j has 0 sample correlation with other independent variables, and as a result of which we may think that there is little multicollinearity among the independent variables, or at least between x 1 and rest of the independent variables. So, this figure actually shows the relationship between variance of beta j hat and the R square from the auxiliary regression of x j on the other independent variables. As R j squared approaches 1, variance of beta j hat actually keeps on increasing, right. We have not mentioned any specific value because it can be anything, but then this shows that R j square approaching 1 increases the variance of beta j hat. Since multicollinearity violates none of the classical linear regression model assumptions, the problem of multicollinearity is not really well defined. It does not define how close R j squared has to be to 1 in order to consider a possible multicollinearity problem, because even if R j square is close to say 0.9, so which is actually close to 1, whether that inflates variance of beta j hat or not, that also depends on the other two factors, that is the variance of the error term as well as the total sum of square obtained from the regression of x1 on the other independent variables. So, because for statistical inference what matters is how big beta j hat is to its variance, just a large value of R j square actually cannot always lead to a large variance of beta j hat. So, it is possible that even if R j square is large, the variance of beta j hat is small because of the other two factors, right. The other two factors could be offsetting factors as well. So, since we have three components here determining the value of variance of beta j hat, of course, one important component is R j square, but then there can be other offsetting factors as well, and as a result of which, since our main concern is on the value of the variance of beta j hat, the problem of multicollinearity is actually not that well defined or well structured. Arthur Goldberger in this context coined the term micronumeracity, which he defines as the problem of small sample size. As sample size increases, standard error tends to 0. Since x1 prime x1 tends to infinity, that is TSS becomes infinity, large or larger. Therefore, in order to avoid the problem of multicollinearity, large sample should be taken. So, one solution is to take a large sample where an increase in x1 prime x1 would actually offset any possibility of a high R j square value. Another way is to consider principal component analysis, which combines related variables into a single variable. Another important point is that a high degree of correlation between certain independent variables can be irrelevant depending on which variable is the focus of our discussion. Okay. So, in economics and finance, control variables are often included in order to isolate the causal effect of a particular variable. For example, in looking at the relationship between loan approval rates and percentage of minorities in a neighborhood, we might include variables like average income, average housing value, measures of creditworthiness and so on, because these factors need to be accounted for in order to draw causal conclusion about discrimination. So, we are actually looking into the relationship or looking at the relationship between loan approval rates and percentage of minorities in a neighborhood. Okay. So, trying to ideally find out whether there is any discrimination in loan approval depending on whether an individual belongs to a particular minority or not, right. So, in this context we also include certain demographic variables like income and the prices of their houses and their creditworthiness, etc. So, income, housing prices and creditworthiness, all of them are included as control variables because they can also impact the loan approval rate, right. Now, they are actually highly correlated with each other, but high correlations among these controls do not make it more difficult to determine the effects of discrimination. because our focus is on something different, right. We need to include these control variables because they also impact and they might have also contributed to the determination of loan approval rate. So, these cannot be ignored. If these are ignored, then that would lead to some other problems in regression analysis, but it is quite possible that they are highly collinear among themselves, of course not perfectly collinear, but highly correlated, but still they need to be included, and that does not hamper our main focus because they are actually control variables and our focused or variable of focus is something different. Statistics designed to diagnose the severity of multicollinearity is prone to misuse because there is no guidelines regarding which value of R j square or variance of beta j hat can be considered as indicative of multicollinearity. Nevertheless, the most commonly used statistic is the variance inflation factor and tolerance. Tolerance is just the reciprocal of VIF. So, VIF for the jth coefficient is calculated as 1 upon 1 minus R j square. So, this is again the regression or the R square from the auxiliary regression of the jth independent variable on the rest of the independent variables. VIF is precisely the term in variance of beta j hat that determines the correlation between x j and the other explanatory variables. So, instead of looking at variance of beta j hat, we are focusing on only that component which is related to the correlation among the independent variables. So, this is given by a measure called VIF. However, the problem with VIF is that there is no benchmark cutoff. Sometimes the value of 10 is chosen, which implies that if VIF is above 10, R j square is above 0.9. A high VIF does not imply that variance of beta j hat is too large, as it also depends on sigma u square and TSSJ. This has already been discussed. Finally, multicollinearity does not violate BLEU, that is best linear unbiased estimator. This is primarily because, as we have mentioned in the beginning itself, that it is actually not part of the CLRM assumptions, classical linear regression model assumptions. So, that is how probably it is actually the problem remains also to some extent less structured. Now, summing up what to do in the presence of multicollinearity, first of all, ignore it if the model specification is adequate in terms of magnitude and signs of the coefficients, and if the aim of the model building is to generate predictions. Because the parameter estimates are still consistent, unbiased and efficient in the presence of multicollinearity, predictions can always be generated, and predictions are always better when we have more and more number of independent variables, regardless of whether they are highly correlated with each other or not. So, depending on what is my focus or goal, I can ignore some certain amount of presence of multicollinearity among the variables. Second is drop one of the collinear variables. So, another alternative is to drop the collinear variables if theoretical and empirical process allows us to do so, that is, it is not a very important variable which needs to be retained in the model specification. Third, transform the correlated variables into a ratio to replace the individual variables. Again, if the theoretical structure allows us to do so. So, instead of having individual variables, we can actually have a ratio of the two variables. And finally, increase the sample size, that is, as it is often said that near multicollinearity is more a problem with the data than with the model. So, model specification actually has nothing to do with multicollinearity. Multicollinearity could be present in the form of data that we collect. Of course, certain variable specifications may entail multicollinearity, but as has already been discussed and also theoretically proved that by increasing the sample size, we can actually partially take care of the problem of multicollinearity, because presence of multicollinearity is going to inflate the variance, and having larger sample size or a large sample size, we can have an opposite impact on the variance. So, inflation in variance will be taken care of by an increase in the total sum of square from the auxiliary regression of one independent variable on rest of the independent variables. So, that is all about multicollinearity. These are the references that I have followed. Thank you.